What I want to talk about now is this idea of population statistics. We've talked about sample statistics, where we get a sample of a population and we come up with, say, a mean that tells us kind of where the data is centering. And then we come up with like a measure of spread, like how spread out are the data values. And so we focused on, to some extent, the mean of a sample and the standard deviation of a sample. Well, we've always talked about samples as the realistic way of getting information because we can't actually test the entire population. So what we're going to talk about now, though, is maybe this is idealistic, but let's say we could measure the entire population. So the population version, these are the sample versions. And then we have the population version. This is the actual mean. This is the thing that's really out there. We just maybe can't get it, but we represent this with the Greek letter mu. And we represent the standard deviation with the Greek letter sigma. Now, there's something important about these. I mentioned it in the last talk. It was about bias. And bias is basically this. And I want to be careful here. I'm going to put this in quotes. If you calculated the mean, if you take a whole bunch of samples, and we'll say we're working with the mean. So we're going to talk about bias and X bar. If we get a bunch of samples, calculate the means, they're actually going to center, they're going to kind of be close to the actual population mean. So we might see like something like this. Here's our mean, X bar 1, this could be X bar 2, X bar 3, the bars on those. First sample, second sample, third sample, maybe this is X bar 4, but they're all going to kind of gather around the mean. Because that's the case, we say that X bar is non-biased. And it means that multiple X bars center around the true mean. Or you could say gather around it. That might be a better word. So that's the idea of being non-biased. Now, when we talk about the standard deviation, it's a little different. If we talk about bias and the standard deviation, what we see in the text is this. The standard deviation tends to come up short of the population, or you might say the true standard deviation. If you take a bunch of these, take a bunch of samples, calculate standard deviations, they tend to underestimate the actual population standard deviation. Not always, but they don't center around it. They don't gather around it. So we say that S is a biased estimator of sigma. And I guess I should say not non-biased for X bar. X bar is an unbiased estimator of mu, the population mean. Again, if we know what that was. A part of the problem, the formulas for sigma and S are a little different. S, as you might recall, was this. Sigma is different, has a different definition. And N here is going to be the population size. Now, what we're going to see in an example is that if we have a sample large enough, we're still going to use S to approximate sigma and use X bar to approximate U. If we have a sample that's big enough, that's what we're going to do in one of the examples here. So there is that. So in certain, what we're going to do is we'll use S for sigma and X bar for mu, at least for large enough and samples. And the book doesn't quite explain what that's going to mean, but at least large enough. So now there is, since we are going to use S anyway, the book does point out an alternative way of calculating S. Now, is this a good way to do things? Well, let's see. Since we are going to use the S, there is a way of estimating it. And it goes like this. S is approximately the range divided by 4. Now, how good of an estimate is this? Well, let's take that data set where we actually calculated this using the formula by hand. So our data was 1, 2, and 3. Now the range is we take the largest value, subtract from it the smallest value. So the range in this case is 3 minus 1, or 2. Now, remember, when we calculated this using the formula, we got an answer of 1, which kind of makes sense. The reason being, again, what S is it measures deviation from the mean, which turned out to be 2. And the way we calculate the mean is we add these up, divide by the number of data points that we have, and then, well, that gives us our mean. And this measures, well, how much deviation is there from the mean? And we got an answer of 1. And so that kind of makes sense. This is 1 unit away from 2, and this one's 1 unit away from 2. All right. So what does our quick estimate come up with? Well, we'll see. So S, remember, the quick estimate is range divided by 4, 2 divided by 4, or, well, 1/2. So when we calculated S like we used the formula to, we got the answer of 1. If we use this slick estimate, we get 1/2. I don't know if that's a very good estimate. So let's try another data set here. So another example we could use. Now this is a data set we're going to be doing a lot with, especially in the next section. What this one was, we're looking at Verizon. This is from the text. Data speeds in airports. So for this one, there are 50 values, And in a later lecture, we might actually list out what these values are, or at least some of them. But for now, we're just going to give some basic breakdown, basic description. The minimum value is 0.8 megabits per second. And in the max, that's 77.8 megabits per second. Now, let's say we go ahead and someone calculated the standard deviation for this. They got a standard deviation using the formula of 16.02. So how does this compare to the estimate? And again, this data set we can look at later. But if we use the estimate, range divided by 4, well, max value minus the smallest value, 77.8 minus 0.8 divided by 4, or 77 divided by 4. Let's see here. And 19.25. Now, this probably compares a little better than before. The estimate we had was a half. The actual calculated value was 1. So that's the actual value was a 100% increase. It doubled the estimate. In this case, the estimate is 1.2 times bigger instead of twice as big. So a little bit closer than before, which is okay, that's nice. So again, you want to be kind of careful with this. Sometimes it could be wildly different. And, okay, sometimes kind of, okay, maybe. So just letting you know. The last thing to mention, well, not quite the last thing, but something else that comes up, and I've mentioned this in lectures before, it's come up in the homework, is when is something statistically significant? And if you remember, there were some homework problems where we had, what was it? It was a pill you take that would possibly change the chromosomes of your baby. And there was what did they come up with? It was something like a 19% chance that the results they were seeing would be results of randomness and not the results of the treatment. And some of you felt that, okay, well, that seems kind of low. So I would say that seems like the chance of this happening by chance is low. So I'm going to say the treatment must be having an effect. And then some of you said, no, 19%, that's not low enough. If there's a 19% chance this is happening randomly, that doesn't seem like the treatment's really making much of a difference. It's just, this is the normal way things go. This is just how this happens. And then the answer was that 19% was too high. And that often in our statistics course, we're going to see that 5% is kind of the cutoff. If there's only a 5% chance something is happening randomly, then, and yet we still see it occur, that's probably some strong evidence that the treatment is causing this and not just the randomness of nature. So there is, and that's what I'm kind of getting at here, that 5%. So they formalize this. It's called the range rule of thumb. And it works like this. Let's say we have our population mean. Again, this sort of idealized value that we wish we could get. If you're one standard deviation above the mean, or one standard deviation below, you're still kind of close to the average. This is pretty close to average still, so we don't consider that being very far from what we normally expect. But if you're 2 standard deviations away, the mean plus 2 away in either direction, then this seems pretty different from what we're used to. So whatever changes we made, whatever treatment we introduced, we're getting some different result. So what we say is this: if your data falls into this range, it's not significant. But if your data falls in the wings, then that piece of data is considered significant. You're far enough away from what we normally expect. Say we did some treatment, and this is what we normally expect when we just go out into nature. But then we add this treatment and we're starting to get results like out here or out here. This is considered far enough away from the mean that, okay, something must have been changed. This treatment's having an effect. That's kind of an assumption we're making. Now, in different studies, depending on what you're doing, it doesn't have to be this way, but this is sort of a rule of thumb that we're using for now. And let me do an example of how this works. Now, this is where, again, I'm talking about that population mean and that population standard deviation that we're not going to know. So with a large enough sample size, we're going to let X bar represent mu, and we're going to let sigma be represented by S. So going back to our Verizon example, let's say we have this. We have a mean of 17.6, and that's megabits per second, moving all these megabits. And then the standard deviation, you'll see it abbreviated like this a lot. Our S, that was 16.02, like it was before. A little more like a 6 and less like a B megabits per second. So let's say we want to figure out whether or not, when are our data values considered significant or not significant. In other words, they're close enough to the mean to where, okay, they're still kind of average. And then at what point do we have something that's like, whoa, that really stands out? Okay, so let's take a look. So for the significant low, we're going to let X bar stand in for mu. We're going to let S stand in for sigma. So that's what we're going to do. We got this, and again, this was a sample of 50 values. So what we're going to say for the significant low, in other words, off here, we're going to do X bar instead of mu minus 2 times S instead of sigma. Again, we're letting X bar and S stand in for mu and sigma. So we're going to get 17.6 minus 2 times 6.02. And so we get our lower boundary. So this comes out to negative 14.44 megabits per second. Now, I'm not a computer science person, I'm not an engineer, and I think when you talk about quantities of data, I don't think you have negative quantities. I've never heard of that before. Maybe it means it's flowing in the opposite direction, I'm not sure. So what to make of this, I couldn't say. So if this is possible, if this is how it's set up, maybe there's some calibration going on here. Anything that's less than this would be considered, well, significant. And we'll talk about more what significant means later. It's not really honing in on the average. Let's look at the high. So that's the significant low. Let's look at the significant high. Well, this will be x bar plus 2 times s. Again, this would usually be mu, and that would usually be sigma. And so we have 17.6 plus 2 times 16.02. And then we get, this one, this might be a little more understandable. 49.64. So if we get data that's above this, we're seeing something that is significantly different, say, than the mean. But again, we'll talk more about what significant means later. So that's how we use this rule of thumb. So just some things to mention about this population value versus the sample value. It looks like bad news for the standard deviation, but there is an alternative that we don't have this problem with. It's called variance. Variance is where we square the standard deviation. And the population version. Oh, I want to forget, we're using mu here. If we're using population, we're using mu over n. The good news here, s squared is an unbiased, not biased, unbiased estimator of sigma squared. So you can use s squared if you want to use an unbiased measure of spread for the, well, variance. Now, the issue the text mentions here is, and it's the same thing that comes up with the standard deviation. So just some things about variance. And we do represent variance as s squared or sigma squared. If we're talking about population, this is sample. Things, little facts about it, factoids. Similar, s squared to standard deviation, x squared is greater than or equal to 0. It's 0 when all data values are the same. So that's the story with s squared. Of course, it's never negative in this case. Increases dramatically. With outliers, just like standard deviation did. And then it's an unbiased estimator. We've got that. The issue that comes up with it, like, why don't they just use this? And the reason is this. The units, this is kind of a star one here. The units of S are the same as the units of data. If you simplify everything down, if you include the units in your calculation and you work it out, and if you square root like inches squared you get just inches. If you do inches times inches, you get inches squared. You can, in a sense, do sort of arithmetic with units that way. Like inches times inches times inches is inches cubed. You can do that. So, all right. The problem, I don't know if it's a problem, but S squared uses, this would be a star, units squared. So when we talk about the mean is in units. X bar uses the units of the data. So here we just have the units as they are, but this one you're dealing with units squared. So you're dealing with some different meanings here. You want to be careful. Inch is an inch, and then like this is an inch. This would be like an inch squared. These are two different things. So that's one reason you might not use this, even though it is an unbiased estimator. So there you go. One last thing to mention here, and it's actually kind of in the beginning, but I'll just say it. We talked about this briefly, and there's not too much to say here with measuring centers of data, you know, where everything congregates or might be congregating, gathering. We talked about rounding. And there's some rounding here also to mention for variation. Excuse me. It's the same thing that we did for center. We round to one more decimal place than present. In the data. So we round to one more decimal place than present in the data. So it's the same guideline that we had for measuring center. We did the same thing for measuring center as well. So that's it. So any questions about this, let me know, and well, have a good evening.